Okay, in this section, I will explain the commonly used Verilog syntax one by one. Before that, let's have a quick review of what we have learned in last section. So, please take a look at the small program here, and you understand the meaning of these statements. Okay, this may be new. The 3 may be new syntax to you. I think all the others you can understand. Okay, let me explain it for you. This is the wait. The ant symbol means wait for something. This is wait for the event to trigger. The event is positive clock. That is wait for the positive of clock, then go to execute the statements after it. So, until simulation time 0, reset and clock is assigned to 0 value, and this sentence will halt the execution of the following statements at this time. Yeah. So A is assigned to 1 at this point, and the random edge after the random edge of clock. What's the meaning of repeat? It's the meaning as the word itself. Do this statement for 5 times. Okay. Do this statement for 5 times. So this is what repeat means. So this statement will wait for 5 positive edges of clock. 1, 2, 3, 4, 5. Yes. After that, A is assigned to 2 and reset is 1. Okay. Then we will wait another 5 clock edges, but it's negative edge. So this is 1, 2, 3, 4, 5. Then the simulation ended. Then the simulation will be ended. Okay, and this is a system call. Okay, this is a system task or function defined by Verilog language. It will return the simulation time. For this case, it will return 100 nanosecond. Okay. And this is the data print format. That is, you tell the tool this data, this variable, this data will be printed in the format of time. This is something like the print syntax in C language. Yeah, in C language. Okay. Okay, let's go on with the Verilog syntax. First, how to declare signals. We call it identifier. So identifier is the names you use in Verilog code, such as signal name, module name, task function name, define name, parameter name, any name. We call it identifier. So you can use these symbols in a name. This symbol, this is underline. But you must begin with the identifier with character or underline. Can't begin with numbers. And the identifier is case sensitive. So for example, these are legal identifiers, and this is illegal. The two are different. Okay, the two are different identifiers. They are different signals. And there is a suggestion for you to define names. Your identifier should be meaningful. reader can get the meaning of the signal from its name. Such as, this is a clock for call block, and this is a reset signal with low active. Yes, low active reset signal. And this is maybe the memory select signal, memory write enable, memory D out, memory D in, and memory address. These names are meaningful. This will make your code to be readable. Then keywords. Okay, there is some words reserved by Verilog language. You can't use it. Keywords you have no use. Yeah, this. There is other keywords. You can find it out in the Verilog standard. I will show you an example. So for the language menu, you can find all of the keywords here. So it seems there is something wrong in the PowerPoint. This is not a keyword, it seems. Okay, you can find all the keywords here. And there must be some explained to them in this menu. Okay, commands. How to write commands? There is always two types of commands. If you just want to comment a single line, use the double slash. It will comment all the characters after the slash to the end of this line. If you want to comment several lines, use this slash with star and end with star slash. So it will comment all the lines between them. And all the comments will be ignored by the Verilog tools such as simulation tool, synthesizer tool. Okay, these are comments. This slide will show you how to define constants in Verilog. Actually, there is three types of constants: constant integer, constant real number, and a constant char. For constant integer, you define it with the format width, single quotation mark, and radix, then give the value after it. For example, you can write 16 single quotation D 100. This means you define a value, a constant value of 100 in decimal format, and it's 16-bit width. So this define is a so this define means the number after it will be treated as hex. So this will equal to 100 in decimal. And the B denotes that the numbers after it will be treated as binary. So this is also equal to 100 in decimal and with 16-bit width. And you can use underline between the binary numbers. So if you use D as the radix symbol, you can write 0 to 9 after it. If H, you can use 0 to 9 and A to F. For binary, you just have 0 to 1. Okay. For real numbers, you just write the real numbers in this simple way. Or you can write it in a powered format. So this symbol equal to the number of this equation. E will be replaced as some power of 10. Also, you can have some constant chars. You can say a string in C language. So they are enclosed by double quotation marks. Okay, enclosed by double quotation, and you write your chars inside it. And each character will be treated as a 8-bit value of ASC2 encoding. So this example, double quotation ABC inside equal to a data of 24 bits, and in the hex format is 616263. Okay, for signal types, then now you have to declare signals. We have learned this before. There is many two categories of signal type: native type and variable type. So for native type, you have learned it has 3 usages. Okay, 3 usages. If you want to declare a late with multiple bits, you have to use this symbol. Then write the first bit index and the least significant bit index here. So this will define a signal of B with 4-bit width. This will be defining a signal of C with 8-bit width. The upper index is 7 and the lower index is 0. After declare of these signals, you can assign value to them. You can use them in some operators, such as the compare operator. And not only wire type, there is also other keywords defining signal with native type. Okay, the commonly used is try 0 and try 1. That means this defines a late with pull down or pull up resistor. So when there is load driven to a late, the late will be pulled down or up to 0 or 1. Okay. But you have to notice that these definitions are not sensitive. Okay, are not sensitive. So you can't use it in sensitive code. It's usually used in test bench. Okay, the other type is variable type. Yeah, it has 2 usages. Yeah, you can assign value to variable type only in procedure blocks. Yes, in always block or in initial block. Well, you can use the value of it at anywhere. So this is some simple code. You can read it by yourself. So please pay attention to this. Rig DC, rig D0. They are all defined as rig type, but this it describes the function of a DFF, yeah, of several DFFs. But this it marks, yeah. So it's this is a sequential logic and this is combination logic, yes. Also called DF as register, okay. So don't be confused with the keyword rig in Verilog. Keyword rig doesn't mean the signal will be synthesis to register. Okay, it can be synthesis to combination logic. Yeah, so you can treat rig just as a keyword in Verilog. The keyword rig in Verilog has no relation with the DFF in real circuit. Okay, this may be confused for beginner. Okay, for Verilog types, there are some other keywords that can declare Verilog type signals, such as real. This is real number. We define integer. Time, real time. There are some examples. Okay. So this, if you define this variable, you can assign value to them only in procedure block. That is in always an initial block. They are variable type. But please note that we usually don't use this type in sensitive code. Okay, you can use it in test bench. Okay, this slide will tell you how to define one-dimension signals. We call one-dimension signals as vector. Okay, you must have familiar with it. Just show it again. Y-dimension signal, we call it as vector. And this is something new for you. Maybe signed. So for signals, if you don't use this signed keyword, default to unsigned value. That means all the bits will be encoded in the original code. Original code of binary. Okay. While if you use this signed keyword here, this will be treated as 2's complement. 2's complement code of binary. Okay, I will show you the difference when they are doing some arithmetic operations in later slides. And you need to notice that they mean treat it as original code or 2's complement code. This is the understanding of tools. Okay, this is the understanding of tools. From the understanding of designer, it's okay for you to define a signal in that format and put a signed value in this variable. That is, you can put, for example, you can put 4-bit 1 in this variable, and you can treat it as in the view of designer, you can treat it as signed value that is equal to -1. Yeah, you can treat it as, the designer can treat it as signed value of -1, but from the tool's view, it will be treated as unsigned value of 15. Okay. So for real number, you can have a real number of one dimension and use it, but this is not sensible. By law, at least by law, this is not sensible. And also you can have char, okay. And you can use char to assign the value to some one dimension vector. Okay, let's see some multi-dimension signals. We call it array. This is something like the array in C language. Okay, you just use this symbol after the signal name. So this is a array of one dimension. This is an array of 2 dimensions. You can define array of 3, 4, 5 dimensions as you wish. Okay, please read the comments after each line and try to understand what the declare means. After declare, you can use it. So for this part, we select one element from this array. Okay. So at this point, you have select one element of 14 bits. Then you use this character to select only 4 bits from this 14 bit. That is the bit 7 down to bit 4. So this symbol can be used to select element. Select the whole element and select some bits of one vector. Yes, can select the element from an array and can select some bits of a vector value. Okay, this is another symbol. Concatenate. So this symbol is used to join bit segment to value to larger bits. Okay, so for example, this means you have selected an element. So this element is 8 bit, yeah, and join with 6 bit 0. So join with a 6 bit 0. This will give you totally 14 bits. Okay, totally 14 bits with 6 zeros on the most significant bits and this value on the least significant bits. And the 14 bits will be assigned to this element in array 1. Yes. So this slide you have 3 new syntax. How to define array, how to use this symbol to select bits, and how to use the symbol to join bits, you can say join bit segment. Okay, you can define signal law and you can use a constant. The next step is to use operators to do some operation on these signals. There are some types of operators in Verilog. The first is bitwise logic operators. So please pay attention to bitwise. Okay. It means if this operator and or exclusion or inverter, if this operator are used in two operands, the bitwise of the result is the same as the input. For example, AB is 4 bit, and use this AND operator, the result will be 4 bitwise. The AND operation will be operated on each bit of A and B, that is bit 0 and bit 0 of B yield this bit. Then bit 1 of A and bit 1 of B yield this bit. This is the third. Oh, sorry, this is the fourth. Okay, the two are the same. Each bit of A and B will be exclusion order. Then the result will be 4 bit and assigned to C2. If this operation is used with only one operand, the result will be just 1 bit. Oh, sorry, there is an exception. This operator is an exception. Okay, this operator is an exception. For this operator, the inverter operator, it can only be used with one operand. For the inverter operator, it can only be used with one operand. So the result of the inverter operation is the bitwise of the result is the same as the input. Okay, just invert every bit of it. For the other three, if it's worked with only one operand, the result is only 1 bit. So that means each bit of the input will be operated using the operator one by one. So for example, AND A equal to each bit will be OR A equal to each bit will be ORed, and the result will be 1 bit. Then there is a whole logic operator, that is take the inputs, or you can say take the operand as a whole, such as these operators. The operation takes 2 steps. First, convert each operand to 1 bit signal. If the operand equal to 0, you can have a tempo of value 1, otherwise you have a tempo of value 0. Then you will do logic operation using this symbol. You will do logic operation on the 1 bit tempo. For example, here A double and B, we will convert A to a 1 bit signal, so it will be converted to 1, and this will be converted to 1, and together. Yes. For this is the same. C will be converted to 0. Sorry. Yes, to 0. And not 0 yields 1. Okay. And there is also some value compare operators. EQ, not EQ. little, big, bigger a EQ, less a EQ. This is something similar to the operator in C language. While in Verilog, there is two strange value compare operators. That is 3 EQ symbol and a lot symbol with 2 EQ symbol. Usually they have the same mean of EQ and not EQ, but they will work differently and data with X or Z bits. So if there is data with 0 or Z bits, the operation of this and this are different. So what's the difference? You can find it by Google, okay? And usually we just use this compared operators in sensitive code. These are only used in test bench. Okay, let's go on with condition operator. You have seen it before. Usually it's used to describe marks. Okay, that is this symbol with this symbol. We have explained it before. The two combine together to get the condition operator. And the concatenation operator. Yeah, you have seen it before. Yeah, this symbol concatenation. It will join bit segment to value of larger bits. And we use this symbol to do bit select. Okay, you can select one bit or you can select some continuous bit. And for bit selects, please note this symbol. It means select from bit 0 and totally select 8 bit. From 0 totally select 8 bit. This is from bit 8 and totally select 8 bit. So the two get the same result and the two get the same result. Okay, at last, it's arithmetic operators. Okay, such as add, sub, multiply, divide, remainder. So you can see the usage here. Okay, for this, you can treat it as arithmetic operator, and you can also treat it as data compare operator. In digital or in digital circuit, these data comparator are usually implemented by the subtract operation. Yeah, let's review. AND of 3 input data. Will it be something like that? Cascade of 2 for AND. Will it be implemented as this hardware architecture? Yeah, if you think so, you must miss something in the first part of this course. Arithmetic data path. Okay, you have to review the first part of this course. It will be implemented as carry, save, AND. Then cascade with only 1 for AND. Okay. Okay. Okay, there is some important notes for you. When you do arithmetic operation, please pay attention to the result overflow situation. Okay, to avoid result overflow, you have to define, for example, you have to define enough bitwise for the result to hold all the value of the operation result. Yeah. How to decide the weights? How to decide the weights of the result? You can think it from the mathematical view. Okay, just calculate. You can just calculate the value range of the operation. Then you will decide within that value range how many bits you have to use. Okay, and try your best to avoid the use of divide and quotation operation. This is also explained in the first part of this course. There is, if you use them, there may be big error, and big delay. Okay, that's all for all the operators. I will end this section here.